Thanks, Michael and others for giving me this opportunity to present. I'm going to talk about some of the work that goes on in my lab. Briefly about myself, you can reach me always at my first name. I have a unique enough first name that I can always find my first name at gmail.com and whatever I want. So that's my email in case you forgot. So I've been educated in 3 continents. I got my bachelor's degree in aerospace engineering from IIT Madras in India, and during that time I also did an exchange program at Politecnico Milano. I came to Stanford for my Ph.D, and that was in mechanical engineering, though mostly dealing with spectroscopy, optics, high temperature systems. Then went to San Diego National Labs as a postdoc, and worked there for a year in diagnostics and other applications in atmospheric area. So in terms of teaching, I've taught 7 different classes at the UCF. Some of the undergraduate courses and graduate courses are listed here, mostly in the aerospace and mechanical engineering field. In terms of achievements, I've been fortunate enough to receive some of them. Been selected as the DARPA Directors Fellowship and Microsoft Investigator Fellowship. We have just this week, we published our 100th journal paper from my group, and more than 75 papers are written by students as co-authors, and we have 1 in science and proceedings of the National Academy of Sciences. The other highlights are I have been honored to I've been very humbled to receive the highest honors at UCF, like the UCF Luminary and Reach for the Stars awards. So the most of my work is in high temperature reacting systems that have applications in space, propulsion, power generation, etc. So you can see, this is a power generation turbine. This is an airplane that has engines, and this is a transportation vehicle that uses fuels. And these are some advanced propulsion concepts. This is a rocket, and you can see fires and explosions. And these are emissions that are coming out of power plants, which burn various fuels. And we have also hypersonics, where you have vehicle development where you get very extreme environment. What is common to all of these systems is that you have a very high temperature environment where you have something that is being chemically converted into some other compounds. In the case of fuels, it's products and emissions that come out. And so in order to understand what is happening in this flow field, you need to have techniques that you can use to understand what's inside that flow field. And in order to do that, you cannot just stick something into this kind of extreme environment, because that will just melt. So we use optical and laser based sensors. And so they work on the fundamental spectroscopy. Basically, you have lasers that are configured to target certain things, and we can relate whatever the laser is measuring to what is in the flow field. And so it's related via the several equations that are derived from fundamentals of radiation. Here is the typical problem that we deal with, and we do everything from every aspect of these kind of problems. You have like an experiment where you measure something where this can be a rocket exhaust, or can be a combustion chamber, or it can be an explosion, whatever. We measure something, and typically what the laser measures is just just like raw data. And in order to interpret that, you need to know what is in the flow field, at least have some idea of what is in the flow field. Most of the time that information is not there, but don't worry, we have the ability to create models to at least train our initial laser selection, and also our strategy to do this problem. And so we do the model development ourselves. And then once we make the laser measurement, in order to interpret that data into, for example, what's the temperature of that flow field, what's in the flow field, we need to have other fundamental data. And so we have facilities like shock tube and other systems that we can use in our lab to gather those kind of data, which are mostly what's the species and their spectral signature at those conditions. Now, this is basically what's happening in all of these high temperature systems. You have a compound at high temperature and high pressure, and it will break down into several intermediates, and eventually you will get the final products. The time scales of this process are very different. The initial steps are happening at the microsecond to millisecond kind of time scales, and you have end products several seconds or hours later. So we need to know these processes, and in order to do that, you need to have schemes to measure those short-lived and intermediates, and also some of the products as they are formed. And in order to do that, we need lasers and also facilities to create those kind of environments. So we have several techniques in our lab. We have multiple shock tubes, and the capabilities of these facilities include going up to pressures as high as 1,000 bar. And this pressure is very high for a typical combustion system, but it's low end for a detonation system. We also have ability to deal with any exotic kind of fuels or propellants, biofuels, and we can also look at high temperature response of, for example, the thermal protection systems. And we we need the lasers, and we also need the facilities to access those kind of high temperature systems. So these are some of the systems that we made, and here they're shown coupled with in this particular case an aerojet rocket dyne facility, where this is our system that we coupled with a rocket engine to measure what's in the flow field. And this shows advanced laser-based systems that are in my lab. Let me show quickly some examples of projects that we did. This is a direct-fired supercritical CO2 combustion, which basically burns fuel at 300 bar pressure. And this shows the pressure versus what is available in the literature. Those are all at very low pressures, and so we were able to go to this extreme conditions. Now, this kind of power generation technology has several advantages. It's a near zero emission. It's a very low cost. It's a small equipment size. But understanding the process at that 300 bar, from a fundamental level, requires new facilities, and we have that capability at UCF. And this shows an example of some of the studies that we did. In this particular case, we are burning methane with the oxygen and CO2, and you can see that without CO2 and with CO2, the burning behavior is different. And this concept of burning fuels with CO2, it's not just in an academic world. This is a Net Power's demo plant that is constructed. It's a $140 million venture that's in Texas, and we actually help them with some aspects of this facility. And this area of projects are funded by ONR, DOE, and several other industries. Now, the conditions that are experienced in a power cycle like this one, it's similar to the newer methane rocket engines developed by Blue Origin and SpaceX. So we can look at similar conditions, using our lab facilities, and we have significant track record, 25 journal papers alone in this area of very high pressure reacting energy conversion. The other examples that I want to talk about, the energetic warheads, and we have explosions. Some of them are benign, and some of them are not something that we want. So you can see that the processes that happen behind an explosion are very different from like a typical candle burning. These two both are burning phenomena, but they're very different. One is very violent, whereas the other one is more laminar and controlled setup. So what is going on inside this flow field? We need to measure that to understand the effectiveness of in the case of a warhead, understanding the effectiveness of the warhead. And in the case of benign applications, you can utilize this phenomena for propulsion. And so the rotating detonation engine is the one such application. And so this shows the temperature measurement that we did inside such an engine, in partnership with the Department of Energy and Aerojet Rocketdyne. The other project which was featured on a UN documentary, it's looking at high temperature thermal decompression of basically chemical weapons. You can see sarin and some similars that are used in sarin, and we were able to study these compounds in our using our facilities. When they break down, there are several intermediates that are formed, and we use our laser-based scheme to track them. And this shows, one example of our model that is basically shows significant improvement from whatever the DoD had. And so they were very happy with, whatever we were able to achieve in this area. And this has been featured in as a cover page article, and also as a documentary by United Nations, and it's available on IMDb. And so it's a movie, so you can say that I'm a movie star. This is an example of a project where it's not a high temperature application. Some of the concepts that we use, we are able to utilize them for space applications. So this is a low temperature application, but follows the same absorption principle that we use in our lab. And we are using LEDs to track trace gases in space environment. We actually built a system, and we flew that in space, using high altitude balloons, and it was launched in New Mexico and captured in Arizona. And so the application is, we want low cost, robust, low mass, low power sensors to track gases in space, and this was funded by FAA. Similarly, the DARPA was interested in project that we did looking at opioid detection. So if you look at these figures, this is showing spectral signatures of several compounds, and this shows fentanyl, and you can see these are all in the terahertz region. You can see that every spectral signature is unique, and so we wanted to target the spectral signature to identify the compound. Typically in opioids, the issue is, they're very dangerous, lethal for person who come in contact with them, and so we want to have a remote detection scheme. And so we utilized terahertz reflectance spectroscopy to remotely say, okay, the compound that is on the table, that is fentanyl or something like a common household substance, sugar, or it's something else. So this particular concept is very interesting to law enforcement officers. And recently, Microsoft reached out to us, and they are also interested in expanding on this area. And so we have a patent that is pending, and we want to use similar technique for COVID-19 detection, and I'm not going to go into the details of that. And here is one example that we are doing for NASA, where the objective is to look at develop low power, long energy propellants for long duration missions. When you have these probes that go out for 20 days in the dark side of the sun, you need a power source. And so we are looking at metallic powders to and control their burning slowly, so that we can extend their burning process for long duration missions. This effort is funded by NASA Space Technology Mission Directorate. In terms of collaborations, the short term, I would like to increase more my involvement with the aerospace and defense industry. We have, even though I've been able to do something, I need to build more on that. And similarly, build on efforts in the hypersonic area. We have been using AI and machine learning for DARPA project, but I now want to do more, of these applications in other projects that I'm doing. And similarly, additive manufacturing at high temperatures have, the applications of our techniques. Hydrogen and low carbon initiatives have been a recent focus for energy conversion. So I want to increase my activity there. Obviously, connecting with other faculty, and wherever they have high temperature application measurement needs. And also educational, improve STEM education and access to minorities. That has been a significant emphasis at UCF and also in our group. Long term, my objectives are to establish centers of excellence or ERC type proposals where you have a long term collaborative effort between academia, industry, and stakeholders, and also target, taking advantage of UCF's proximity to Kennedy Space Center, get more involved in lunar and planetary and deep space research. Obviously, the acknowledgement cannot be, will not be complete in the short talk. But I, want to thank my chair, dean, and the associate VPs of research, MA staff and faculty, and office of research personnel, and several internal and external collaborators. Currently, my team members, we have one postdoc, one research associate, and several PhD students. And previously, I graduated about 10 PhD students, and they are in academia, national lab, and industry. We have been funded by pretty much every federal agency except NIH, AFOSR, DITRA, DOE, DARPA, NSF, FAA, NASA, ONR, etc., and several industries. And that's where I stop.